the next speaker in the list, Professor Ilyichov from Moscow.
So the purpose of this investigation is to give more or less comfortable theoretical description to possible observations of wave events on the water surface under an ice cover in natural bases, say oceans, seas, and so on. There is lakes, big lakes, and so on. The descriptions via the full equations is too cumbersome for practical applications. It should be noted that waves under the elastic ice cover cannot have large amplitudes due to understandable features. Big amplitudes may cause the disintegration of the ice cover. So we are restricted usually to the small amplitudes, and even in practice they are small. And so a good candidate of the theoretical descriptions of these waves is weakly nonlinear governing equation. And we compare the parameters, and we compare in the present speech, we compare the parameters of envelope solitary waves via fully nonlinear and weakly nonlinear descriptions. In case they are similar, we can use the simple weakly nonlinear equation to describe our practical observations. So the aim is to describe the possible description of practical observations which are unknown and which take place in, say, in Institute of Arctics and Antarctics in your town. We use this simple Kirk of Love model for the ice cover, the ice plate of Kirk of Love, and the pressure of this plate is given first by the initial pretension or initial pre-stress in the ice cover. H small is the thickness of the ice cover. A is the curvature radius. M is the momentum, and it is expressed from the longitudinal stress as shown here. Eta is the deviation of interface between the ice cover and the water surface, the water, the layer of water to be treated, and the ice cover, the ice plate, floats on the water surface. G is flexural rigidity, and that's all. Yes, and rho S is the density of ice, the density of the elastic ice plate, the material of the ice plate. The fluid occupies the layer between the layer with horizontal bottom, and the surface is given by H is the depth in the initial state of the water layer. Eta is the surface deviation, the surface of the water layer. So the coordinate Z is the depth of the surface layer, and on the surface it is given by this equation. Next, so we use the usual fluid equations, the Euler system for the potential movements. Phi is the potential. Then in the Cauchy-Lagrange integral, we have the additional pressure due to the elastic plate. This pressure is caused first by the pretension in the ice, the initial stress in the ice. then by the flexural rigidity itself, and also by the surface deviation, the interface between ice and water. The constants used here is given here, and K is the kappa 1 is the pressure due to the kappa 1 is here is due to the pressure is due to the pretension, and K2 is the pressure due to the flexural rigidity, and the frequency, the dispersion relation is given here. The expression of frequency via the wave number. We are looking for the traveling waves propagating in such a system. So first we, as usually, dimensionalize the variables. V is the velocity at a surface deviation, and then we have three constants, the basic constants of the model. First, the opposite to the square root number, lambda, then beta, the analog of bond number for the capillary gravity waves, and gamma is the dimensionless flexural rigidity, and the constants C and K, kappa, which characterize inertia of the ice layer, and usually they are neglected because the inertia of the ice layer of the ice plate in comparison with the inertia of the fluid layer is small. These equations, the equation for the traveling waves propagating, say, to the right, supports the bifurcation. So in the parameter space, we have in particular one certain surface where the bifurcation takes place, where our system of equations for traveling waves in the neighborhood of this surface can be written in the form shown here, in the operator form. A is operator, U is the vector function, point denotes, upper point denotes the differentiation with respect to longitudinal coordinates, AX. F is nonlinearity. Mu is the measure of deviation from the surface. How far we go from this surface in the parameter space. On the surface, we have the bifurcation. This is bifurcation surface. The eigenvalues of the operator A come in pairs to the imaginary axis, and to the right of the surface we have the following distribution of eigenvalues in the neighborhood of the imaginary axis. We have this distribution results to the appearance of the envelope solitary waves, and to the left of the surface we have the solutions of quasi-periodic, periodic, and so on. So we have the Centromere Theorem also, and it's a long history how this theorem applies, and I stress only the sense of this theorem. The meaning of this theorem is the following: that the infinite dimensional vector function U, of which unknown function of the equations can be decomposed into two parts. The first part is finite dimensional, u0, and the other part is finite infinite dimensional u1. And the infinite dimensional can be computed as a function of the finite dimensional part of this equation. In other words, the infinite dimensional equations in the previous slide, which is given, this one, x point is the differentiation with respect to x. A depends on the derivatives of with respect to the width of the layer. We can reduce our system infinite dimensional to the finite dimensional dynamic system. In our case, the dimension of the system is 4. And this is locally in the small vicinity of the bifurcation surface. And this system is maybe integrated to arbitrary order in mu. And we can compute the solution of the system, and it is given, say, its envelope solitary wave solution with phase and group velocities equal. They are equal, namely the filling of this envelope propagate with the speed which is equal to the speed of the envelope itself. And we can, using our nonlinear formulation, we can estimate the length of this wave, the amplitude, of course, and the velocity of this wave. And to compare this description, which is given by the fully nonlinear treatment, with the weakly nonlinear equation, which can be derived. In this case, this is the third order Schrödinger equation with certain coefficients, which can be computed. Say the frequency is given by this formula. Beta V W and gamma W are dimensional bond number or and flexural rigidity of the ice plate, and we can estimate the length, say, and the velocity of the wave in this case, of this solitary wave, which via this description, the special solitary and envelope solitary waves with phase and group velocities which are equal. And here is the comparison. Here Q is a dimensional wave number, and we see that the larger depth of the fluid, H capital, depth of the fluid, H small, the thickness of the ice cover. The greater the depth of the fluid, the shorter the wave. Yes, and so Phi and T is fully nonlinear treatment, and V and A is weakly nonlinear approximation, treatment via nonlinear approximation. And we see that the length of waves for several depth and several wave ice thicknesses quite similar, yes, and velocities, speeds also quite similar. Therefore, we can even I should mention that it's valid only for not large depth, because I stressed that the greater the depth, the shorter the wave. And our approximation, weakly nonlinear, works when we treat the long waves. Long waves in the sense that the certain ratio is small enough. And for the moderate depth, we see the good, very good coincidence of the wave lengths and velocities of the wave. It means that we can use our weakly nonlinear approximation for the waves which can be detected, which has certain velocities and certain lengths for certain depth of the fluid and thicknesses of the ice. And for some, for not large depths, we can use weakly nonlinear approximation, which is quite simple, unlike the full approximation. So, in order to describe the observed data theoretically, we may the reason of this analysis that we may use as the governing the simple third order Schrödinger equations with certain coefficients for the description of the observed data. So I think that I can finish on with this. Thank you very much.
Thank you. Thank you. Questions, please. I don't see. Okay, so I have a question. Am I right that the ice you consider the ice as a flexible? So
flexible elastic plate, yes.
So it's not broken.
Not.
Oh, okay.
It's uniform elastic plate, Kirk of Love. And non-linear, geometrically non-linear, but physically, of course, linear because of the Hooke's law takes place.
Okay. Any more questions? So, if no questions, thank you very much again.
Thank you very much.